Okay, thank you, Minhai and Si for the kind invitation. So my great pleasure to give a talk in this conference, even though I cannot go there. Today I will talk about a joint work with Ricardo Alonso and Yoshiori Momoto, Wei Yang Shun. Okay, and then the main film that I would like to present today is that to show that in the perturbative framework, okay, so if we assume the initial perturbation, if the weighted L infinity norm is small, then the solution exists in the same function space. Okay, so this the approach is new compared to the existing approach for existence theory in the perturbative framework. Okay, so this is the main result. So all of you are experts, so I don't think I need to talk about the equation. So before I go to the L infinity solution, I would like to recall the work on the L2 first. Okay, so both these two results, in fact, are for perturbations with algebraic decay tail in the velocity variable. Okay, so even though the backstay is Gaussian, it decays exponentially, but the perturbation has a much slower decay. So these are the three collaborators, Alonso in Texas A&M, Qatar, and Morimoto from Kyoto University, and Wei Yang from Simon Fraser University. So this is the equation we all know, the Boltzmann equation. And then the purpose of these results are for the case when this cross section B has singularity, angular singularity. Okay, so the angular singularity, in fact, is assumed to be in this form. So it has two parts: kinetic part, V minus V star to the power gamma, and we assume that gamma is positive, so we consider only the half potential case. So the singularity in the angle covers the full range. Okay, so the power of theta is -2 minus 2s. So in the results, we consider the case when s is between 0 and 1. Okay, so this is motivated by the inverse power law and so on. Okay, so now there are a lot of work. Okay, here only this very few about searching for function space with very minimum regularity in space variable x. Okay, so in a bounded domain, there's a series of work initiated by Yan Guo using the L2 L infinity approach. So a lot of very good results. And then in the whole space, we started many years ago with Alexandra Morimoto, Seiji Ukai, and Chaojiang Xu, and try to show that the perturbation, if the perturbation is in HXS, S is greater than 3/2 because it's 3 dimension, L2 in V, and try to find the global existence. But at that time, we failed and only got the local existence. Okay, so recently there's a very interesting result by Renjun Duan, Shuangqian Liu, Sakamoto, and String. Okay, and they use the this function space, use the linear algebra in X. So they take Fourier transformation in X and take the summation after taking the supernorm in T. So using this norm, they can show that the initial data is bounded in this norm, and then solution is also bounded. Okay, so well posed this. So in all these results, okay, including some others that I didn't mention, is based on this inequality. Okay, so you need to find a norm such that the space is algebra. Okay, because the Boltzmann equation is nonlinear, so you have F times G. So in this norm, you have this kind of inequality. Okay, so and then use priority bound functional construct some functionals, and then to cause the boundaries of the perturbation in this kind of norms. Okay, and then for L infinity, if we take x to be L infinity in x, and this kind of estimate is missing for Boltzmann equation without angular cutoff. So off this is true. This is a work by Seiji Ukai long time ago. Okay, because if you assume the angular is cut off, then the linearized operator can be written in two parts, a multiplier operator and compare operator. Okay, then you can write the equation in a mild form, and then you can take L infinity norm and so on. Okay, so this can be done. But we all know that if the condition operator is singularity, then you cannot decompose the gain part and the loss part. Okay, so this kind of decomposition does not exist. Okay, so this is the difficulty. So the Boltzmann equation without angular cutoff is still valid in L infinity function space. This is the goal. Okay, so so our approach is slightly different in terms of analysis. The approach is different from the previous work. Okay, so what we did is the following. Okay, instead of apply the algebraic structure to cause the bootstrap argument, the idea is to apply the Giorgi argument to first work on the L2 estimate on the level set. Okay, and then use a localized strong averaging lemma. Then combine these two estimates, we can construct a functional so that the Giorgi argument works. Okay, and then it will give us the infinity estimate on the perturbation. Okay, so the L infinity estimate on the solution is obtained by using this approach. Okay, so I will elaborate this a little bit more later. Okay, so now the Giorgi argument for PDE and kinetic equation. In fact, there are a lot of interesting work. Okay, I'm not mention all of them here. So here I just mentioned for the diffusion equation, there's a paper by Caffarelli, Verschuur, okay, long time ago. Okay, and then for kinetic equation, for example, Landau equation, Fokker-Planck equation, when the kinetic operator behave more or less like a Laplace. Okay, so there's also a lot of work by Guillaume and Gauss, Inber, Mo, Verschuur, and Kim, Guo, Huang, and Mo, Hart. Okay, and then in all this work, they show the Hodder continuity. Okay, and also the Hahn inequality and so on. So for Boltzmann equation, there's for space homogeneous. There's also a work by Alonso 2 years ago. Okay, so the difference, there's some difference between the Landau equation, Fokker-Planck equation, and the Boltzmann equation. Okay, because the Boltzmann equation basically is a singular integral operator. So even though it has some kind of gain of regularity, but this can be achieved. Okay, can be not directly, just like the Laplacian, but through the strong averaging lemma. So before I present the result, I also would like to mention there's a big difference between the perturbation in the Gaussian tail. So this is the standard decomposition. The background Westphalian is square root of mu times perturbation little f. Okay, so if you simply write the decomposition as mu plus f, and f only has some kind of algebraic decay. So the estimate, the analysis is very different. Okay, so for the later, for this algebraic decay, in fact, with angular cutoff, there's a very important progress. Godani, Mishler, and Mo, okay, 2-3 years ago, published, but was online for many years. And then about the spectrum gap, okay, in some abstract Banach space. So without angular cutoff, there's also two groups of people obtain the result, okay, a Horn, a Toron, a Tristani for mild singularity, and we also did the case for the strong singularity, okay, cover the whole range when S between 0 and 1, okay. So here's the short presentation about the difference between the Gaussian decay and the algebraic decay. So if we assume the solution is can be written in this form, then the linearized operator is a standard self-adjoint, and then you have a very good strong coercivity estimate for without angular cutoff, okay, because this arbitrary norm f L mu f in fact give you the gain of regularity s. S is the parameter in the angle, and also gain of moment. Okay, so it's strictly negative. Now, if you only have polynomial decay, f is mu plus f, and then the linearized operator is no longer self-adjoint. Okay, so the coercivity estimate is much weaker. Okay, so all you can show is that this quantity has a very good coercivity term, give you the gain of regularity, but no gain of moment. Okay, because the gain of moment in fact comes from the difference, the differentiation of the Gaussian. Okay, but for algebraic decay, you don't have it. Okay, so error term, okay, L2, and gamma O2 comes from the kinetic part of the cross section. And in fact, in this analysis, you will find out that this integral plays an important role, okay, in the analysis. You cannot use simply the HS norm with weight. Other than that, you have to use this good term, okay? So this good term is not equivalent to the HS norm, okay? Because the weight is slightly different. The upper bound and lower bound is different, okay? But with this, you can indeed post the weight, okay? So now for L2, the film can be stated as follows, okay? So if L2, if we assume the we have regularity, strong regularity in space variable x, so that means the second order derivative in x is bounded, okay, with some weight. Okay, so let's don't worry about the weight at this moment. And then the film can be stated as follows. Okay, so we can say that when the parameter s is between 0 and 1, gamma also between 0 and 1. So if the weight is the decay, algebraic decay, the parameter is big enough. Okay, so if the perturbation is small in this L2, H2 in X space, and contains no macroscopic component, okay, in average, then the solution to the Boltzmann equation exists and converge to the equilibrium exponentially in time. Okay, so this is the L2 theory. So the question is whether we can remove or replace the H2S, H2X by L infinity in X. Okay, so this is the question we want to answer. Okay, so to prove that film, in fact, there are three main components. Okay, the first component is to show that the moment can be propagated in time. Okay, so you always, because the net of strong coercivity estimate, so you always have this kind of error. So but it can still propagate in time. Now, because the singularity, the semigroup generated by the linearized operator, in fact, gives the gain of regularity h negative s. Okay, so the L2 bound on solution to the linearized Boltzmann equation, in fact, is bounded by the h negative s norm on the initial data. Okay, of course, the coefficient depends on square root negative 1 over square t. Okay. The result by Godani-Mishler-Moe for cutoff holds for long cutoff, this spectrum gap. Combine these three estimates, then we can prove the film I just mentioned. Okay, so the idea is how to, now the question is how to relax this h2x to L infinity, because h2x is too strong in some sense. Okay, so this is the film we want to prove. Okay, so the let me see. No. I see. This is the okay. This is the film I would like to present today. Yes. So so the same assumption on the gamma and s. Okay. So if we assume the initial perturbation, okay, f naught minus mu, the perturbation is bounded in L infinity and L2, okay, with some weight, okay, for example, K naught. This is small. And then for higher moment, it is bounded only, okay. And K naught and K, I don't think I have time to talk about it, but just some numbers, okay. Then you can show that the solution exists, capital F, and the solution in both L infinity norm and L2 norm exponentially decay to mu. Okay, so this is the main film. Okay, so how to understand the proof? So let me look at this this chart. Okay, so the main idea is not to show that the L infinity norm has the property the solution is bounded by initial data and itself squared. Okay. Other than that, we first assume maybe locally in a very short time the supermom in both x and t, the L1 norm of perturbation is small. So this is assumption we need to close it. Okay. So under this assumption, then we can perform the L2 estimate. Okay, so you can obtain the L2 estimate and also the L2 in HS in V estimate because of the singularity in angle. Okay, and the similar estimate can be performed also on the level set of the solution. Okay, now with these two L2 estimate, one can apply the averaging lemma that I will talk about it later to have some kind of gain in x variable. Okay, so you have HS prime L2 in V estimate on both the solution and the level set. Now, based on this L2 estimate and also the XS prime estimate, and one can construct a functional on the level set and then apply the Giorgi argument to show that in fact the solution is bounded in L infinity norm. Okay, and this norm depends only on the initial energy. Okay, so then you can close the loop. Okay, in some sense. Okay, so this is the idea. Okay, so to prove to achieve this, there are three main steps. the first step is the L2 estimate on the level set. Okay, so here I just give you the statement. Okay, so so the statement says the following. Okay, so suppose this capital G is mu plus little g. You can view little g is given, and f is mu plus f. Okay, f is the solution we are looking for. Okay, so for this capital G, we assume it has this satisfy these two properties. Okay, so these two properties are in fact crucial, because with these two, one can have the uniform coercivity estimate. Okay, L1 bound and L log bound. Okay, now under this assumption, so if the weight is sufficiently large, okay, and this FLK plus is the F with the weight V to the power L minus K, the positive part. Okay, I think I wrote it somewhere. I wrote it somewhere, I forgot. Sorry. And then so you can have this. Yes. So to have the L2 estimate on FLK plus, okay, this term, the level set component, this is the F greater than K, okay, with the weight, of course. Then to do this, we multiply both sides by this quantity, then you have to estimate Q times this one, okay. But under this assumption, you can show that in fact this is has upper bound. This upper bound can be written like this, okay. So here you can see that it involves the L1 bound on the little g, okay, L1 bound on the little g. And then, but by the assumption, okay, the loop, the chart I just mentioned, this quantity we assume it is small. So this is small, okay, small. So you have a very good term, okay. So this is the error term, and then somehow with this, also the assumption you hope you can expect you can cause the L2 estimate on the level set. Okay. Now to apply the average lemma, then we also need the L1 norm on the condition operator. Is this one, okay? So we need to show that for the same setting, G and capital F, capital G and capital F, then with all these parameters, okay, this kappa is greater than 2. Okay, so we want to show that this integral, okay, has a uniform bound as like this. Okay, so in fact this is true. Okay, this is true, can be proved. We put extra negative derivative in V on this part because we need to kill the singularity in Q in order to have a uniform estimate. Okay. Now with these two estimate, then we can with this estimate we can apply the famous average lemma. Okay, so here's the just a list of the velocity average lemma was introduced by Gauss, Tom scientists in 80s. Okay, so there's a lot of work in different function space and improvement. Okay, and Gauss, Lyons, Tom scientists, and so on. Okay, and also Bouchot, David, and Gauss, Masrud, Parenti, and Patan. So here, I cannot mention all. Okay, so here I would like to say that what we need is the localized in time version of the estimate obtained by Bouchot. Okay, in 2002. Okay, so the estimate can be stated as follows. Okay, so if we consider this kinetic equation ft plus v dot gradient xf equals the source term. So if we assume that we know that the solution has some regularity in v variable belongs to LP, and then you can always find this is flat, okay, a small number defined like this, okay, so that the following estimate holds. This one. So this estimate holds, okay. So you have gain of regularity in x and t, okay, and it is bounded by the solution at the two endpoints because it's localized in time, okay, and then also the source term, okay. So this f theta basically is the q we are looking for, okay. So now with of course there's also some extra term on the LP. Now assume we assume that all these estimate holds, then we can construct a functional, and this functional contains the L2 norm on the level set and the HS norm in V on the level set comes from the coercivity, and also the LP norm of LP norm S double prime WP S double prime in X. This term, okay, comes from the Evervision lemma, okay. So now if we work on this functional to see how it evolves in time, then you can show that the functional in fact satisfies this inequality, okay. So this part, this is the take the supermom in T. So if we without taking the supermom, you can show that when T2 is greater than T1, and this functional is bounded by initial data LP norm and plus this term, okay. So this term, the important part is that this power beta I is greater than 1, okay, and the AI of course is positive, okay. There are several terms comes from Q and the commutator and so on. So there's a summation in 4, okay, and this is homogeneous in K. Now once we have this estimate, then we can take the supermom in T between T1 and T2. Then we have the estimate. Press the wrong button. We have the estimate on the function. Okay. So here, let me introduce some notations. Okay. So let's choose a K naught to be sufficiently large. Depends on initial data. And MK is K naught minus 1 minus 1 over 2 to the power K. Okay, K is from 0 to infinity. So when K goes to infinity, it's K naught. So if we define the level set Fk to be F minus Mk with weight positive, and the functional I just defined is for Mk 0 to T. Okay. Denote this by Ek. Then with this estimate, estimate on the functional, then we can show that the Ek in fact is bounded by the initial data plus Ek minus 1 to the power beta over K to the A. Okay, but beta is positive. Beta is greater than 1. That's the key point. So for the first two terms, it's easy because K naught can be chosen large enough so that the level set for the initial data is 0. Okay, because the initial data is assumed to be bounded initially. So we end up with this inequality, very inequality. So Ek is bounded by this summation. Okay. Now, for once we have this, then it's almost done because it's done because you can construct a E star to be this quantity, and then you can show that the E star satisfies the E star K satisfies the opposite inequality, the inequality in the opposite direction. Okay, so you can compare by comparison argument, then you can see that the EK is in fact is bounded by EK star. Okay, and what's EK star? EK star by our construction goes to 0 when K goes to infinity, because EK star, this Q naught is greater than 1, because beta I is greater than 1. Okay, so this is less than 1 over Q naught to the power K. So when K goes to infinity, E star K tends to 0. Okay, so we have the level set, the functional goes to 0. So the level set, the L2 norm goes to 0, and then this implies the give you the L infinity bound on the solution. Okay. Now, so far this argument up to this point is very locally in time. Okay, very locally in time. So basically, once you have the local in time estimate by the spectrum gap, then the result holds for arbitrary time. Okay, so by the spectrum gap, and then combine the local L infinity estimate, then we have the L infinity bound on the solution globally in time, and also have the exponential decay in both L infinity and L2 long. Okay, so this is the end of my presentation. So thank you.
I have a small question. Maybe.
Okay, thank you. Hi. Well,
hi, Tong Yang.
Hi, I can hear.
You can hear me? Thank you for the nice talk.
Yes. Thank you.
I wanted to ask you two small questions. The first one is, so if I understood your talk correctly, you give the first L infinity perturbative solutions in the non-cutoff case. So that's you improve the perturbative theory by just using L infinity as the space for the smallness, right?
Yes.
Do you think if I'm just comparing with the Navier-Stokes theory, which you could imagine that your theorem could be connected to the Navier-Stokes theory by fluid limit. In Navier-Stokes, we can go below L infinity. I'm just wondering if you thought about that, if you think you could go to some LP, and if it's possible to go to some LP, then there should be a critical P, maybe a smallest one, so that the perturbative problem can be solved in a well-posed way. So that's the main question, and maybe I just said the second one because maybe you can answer both at the same time. I was just wondering whether part of the estimates you use are similar or not to those in the recent papers of Cyril Imbert and Luis Silvestre on the non-cutoff Boltzmann equation. I mean, I'm not compared really. I was just curious.
Thank you for the question. So for the first question, I think this is a very good point. So in fact, the L infinity is not necessary. Okay. So, but I think the argument also was for LP. But for the Boltzmann equation, I cannot find the critical LP. So this is the yes. So let me see. So this is at one point I try to understand this LP, replace this by LP, but I don't have the precise statement. So this is a very good point.
But in principle, your method can go a little bit below L infinity. In principle,
I think so. Yeah, in principle, yes.
It seems to me as well. Yeah. Thank you.
Yes. Yeah. Thank you. And then for the second question, I don't know which paper you refer to.
You can look at, well, there are 2 or 3 papers. It's a series of papers. They are not really focusing on the same goal as you do. So they prove similar things. I participated this program more on the Landau side and a bit with on the moments for Boltzmann. The idea is to prove a priori, conditional regularity. Any solution that has, but so it's not exactly the same target as you.
Yes, you're right. I know those papers. They are about the regularities rather than the existence.
Absolutely. So they don't prove the same theorem as you, but I was just curious because the estimates, the Giorgi estimates, are similar to the ones you use, it seems to me.
Oh, I see. But yes. So, for example, for the solution, we obtain in this framework how to show that it is C infinity. I think is still not covered by
the C infinity. This is definitely covered in another way in their work. You should have a look. Yeah, what they do not cover for sure is your theorem of perturbative solutions, the global existence of perturbative solution in low regularity space, because they do not focus on the perturbative theory. They do the Giorgi Schauder and infinite bootstrap to get C infinity.
Right. I know. Somehow I read their paper, and then they mentioned the result covers the solution, for example, obtained by Don Liu strain. Yes. But anyway, we can discuss this because this is not okay. Thank you.
Thank you.
There are a couple of questions by Francois Goals on the chat room. Can you read it? Can you see it, Tom?
Oh, yes. Here you use the Deterge only for. Oh, yes. We only use the. You're right, Francois. So we only use the Deterge argument for L infinity bound, not the regularity. I know that for your work on the Landau equation and Fokker plan, you have the order and so on.
Yeah, I'm sorry. Hi, Tong. I'm sorry I missed your answer.
No. Oh, sorry. So yes, we only use the Deterge argument for the L infinity bound, not like the for the Landau or Fokker plan for order inequality and so on.
Yeah. But do you think it will be useful in this context to try to push the? Do you think it would be possible to push the Giorgi argument a bit further in order to?
I think so. Yes. I think it's possible to use oscillation numbers and so on.
Okay.
Thank you.